Okay, great. So hello everyone, thank you for attending our session. Mariana and I are both master students at INRS located in Quebec in Canada. Our project focused on the evaluations of the geothermal potential of abandoned and flooded open pit mines, considering the thermal energy resource and the geochemical aspects. So, okay. So the geothermal potential event on underground mine is well known for their great potential of heat extraction because the water contained into the galleries is maintained at relatively high temperature by the thermal interaction between the surrounding rock and groundwater flow. But on the other hand, the geothermal potential of open pit mines is often overlooked. But with their large volume of water available, maintained at low temperature, they have also great potential, but now for cooling applications. So in our presentation, we will discuss about the estimations of available thermal energy resource, and it will be followed by Mariana's project with geochemical and physical chemical considerations, both specifically for open pit mines. Okay, so Mariana and I have two study sites, Carey Canadian and King Beaver mines. Both are abandoned and flooded open pit mines located in Thetford mines in the southern of the province of Quebec. So Thetford mines is a city well known in the region for its past mining activities associated with asbestos extraction. And the territory is now shaped by abandoned and flooded open pit and underground mines. So because the population is growing around these sites, that makes the geothermal resource more accessible, more interesting for residential and industrial sectors. So note that in our presentation, we will discuss only on the work done on Carey Canadian site, but everything explained is also replicated on King Beaver mine. So let's begin with my research project. I will explain to you how I estimate the available geothermal resources in flooded open pit mines. So, okay, first of all, unlike underground mines, several heat transfer mechanisms arise from the interaction between the water contained into the open pit and the atmosphere. The evaluations of the geothermal, the thermal energy can be evaluated with the volume method, which is considered the volume of water available, the volumetric heat capacity, and the difference temperature between the initial and final temperature after an exploitation. In these presentations, I will present the results by the thermal power, which is considered represented by the thermal energy divided by an operation time, which will be 25 years in my case. So the available thermal power will be then deducted by the thermal power absorbed by the compressor of the geothermal heat pump to represent the energy that can be supplied for buildings. So in my study, the processes considered in my thermal balance is the available volume of water, which can be represented by a static energy, and the rainfall, the groundwater, the runoff, and the surrounding rock, which can be represented by dynamic energy. So I will show you the method that I use to determine the volume and the temperature of the water contained into the open pit and for the water supply, and I will show you how I evaluate the volume, temperature, and thermal properties of the surrounding rock. So for the volume of water contained into the open pit was evaluated by a bathymetric survey conducted using a Garmin EcoMap sonar. All of these data was then processed with a geographical information system, which allowed me to determine the water volume around 23 million cubic meters inside the pit. The temperature of the water contained into the pit was evaluated by using a buoy system, which retains 100-meter long cable vertically into the water, on which a series of temperature sensors were attached. The main objective of this system is to record continuous temperature profile of the water throughout the year. So to make it possible, every sensor recorded the temperature of the water every hour for a full year long. So all of these data allowed me to produce this graph, which is make it easy to visualize the effect of the summer seasons, here characterized by warmer temperature, and the winter seasons characterized by colder temperature. So the average annual pit water temperature is evaluated around 5.25 degrees Celsius for the entire pit. The water supply volume was evaluated for the pit by a hydrogeological balance with the turtle weight method. It is assumed that all precipitation that falls into the mine's watersheds will enter ultimately into the pit water by direct rainfall, surface runoff, and groundwater flow. So the initial temperature of the rainfall and the runoff is considered to be equivalent to the ambient temperature, which is different for each month. And the initial temperature for the groundwater is considered to be constant during the year, which is equivalent to the understood ground temperature. Okay, now, so for the volume and the temperature of the surrounding rock, there are more difficult parameters to determine. So to do this, I use this formula, which is characterized as heat transfer by conduction in a solid, in a one-dimensional semi-infinite domain, and in transient state. So the principle is to evaluate the temperature propagations in a solid in time if there is a sudden change in the temperature conditions imposed at its surface. So to apply this principle to characterize the heat transfer from water to rock, the initial temperature, the distance before that, the distance of the temperature propagation must be determined for each axis of the open pit, because the initial temperature will act as a boundary conditions and will vary in function of the spatial component of the geometry. So the initial temperature of the rock in the horizontal components is, so for this case, is considered fixed regardless of the distance and equivalent to the annual average temperature of the water. The initial temperature on the vertical component for this case will vary with the distance according to the geothermal gradient, which will have an effect on the distance of the temperature propagations. So if I want to evaluate the volume of the rock, I assume a simplification of the geometry of an open pit by using a half ellipsoid form. And in principle, we can expect that the amount of the energy extracted from the rock will decrease as a function of a distance. So the maximum distance of the extent of the temperature propagation is established when the temperature difference is equal to 0. So if I want to evaluate the contribution, the energy contribution of the rock in function of a distance, I divided the volume in several bands for which the temperature, so the initial and final temperature, will be based on the distance. So this is why the energy contributions of the rock corresponds to the summations of all of the years. So finally, the energy extracted from the rock is less significant during the first years of operations. And so it is more representative to consider the average of the energy contribution. So if I assume the volume and the thermal properties of the rock fixed, I can represent the average of the energy contribution by delta T divided by 2. Okay, so the thermal properties of the surrounding rock are determined by rock sampling in the field and with laboratory analysis with a thermal conductivity scanner. With 20 rock samples collected around the pit, I evaluated the average thermal diffusivity around 1.4 minus 6 square meter per second, and the average volumetric heat capacity around 2.7 megajoule cubic meter per Kelvin. Okay, so finally, If I consider an operating temperature of 25 degrees Celsius, so here and here, and an operating time of 25 years, like I said before, the available thermal power on the Canadian sites must be evaluated around 5.96 megawatt. And the thermal power of the mean water only, the mean water volume only is around 2.4 megawatt. And with the method that I show you, I can evaluate the contribution of the surrounding rock around 19% of the energy of the water volume, and an annual contribution of the water supply around 5% of the energy of the water volume. If I consider the energy consumed by the compressor of the geothermal heat pump, I can evaluate the thermal power available for buildings around 4.84 megawatt. So this is the end for my part, so I will hand over to Mariana.
So hello, everyone. My part is, I would like to go through the first geochemical characterization of Canadian beat. But first of all, why is geochemistry important? As we're working with a project in of an open loop heat pump system, we are dealing with a pit water that is the thermal fluid. So this water flows into the system and it has its own physical chemical properties. From literature of several heat pump system applications in groundwater studies had shown significant mineral precipitation due to mixing different redox conditions, causing pipes clogging within days or even hours. Moreover, systems like those create heat plumes during injection. So during its operational time, water temperature will also increase. So that has raised two hypotheses. If we induce mixing in different water column layers, would that impact the redox process and finally clog the pipes? And if so, the rising of temperatures water could also have thermal effects on biogeochemical reactions. The pictures I'm showing are from the buoy system installed, as Samuel showed earlier. The temperature sensor were arranged in metallic alloy cables. And when we went to retrieve them in 2022, twice, each time 6 months apart, we noticed mineral precipitations all over the cables. So therefore, understanding how the dynamics of this environment work may give us some clues for better design the system and increase its sustainability. Lakes around the world usually have its dynamics controlled by seasonal variation, wind stress, thermal stratification, salinity, and ice formation. A seasonal pattern of thermal stratification, as Samuel showed earlier, also in the temperature profile, is common in most temperate lakes. So this thermal stratification is a process that results in the separation of water based on its density. The maximum water density is at 3.98 degrees Celsius. So olemitic lakes like those here that I'm showing, they experience at least once complete overturning within a year during autumn and spring times or spring. And what is the trigger for the lake to overturn? For example, during between summer and autumn, the top layers here, the top layer here, start to get colder. Layer reaches 3.98 degrees Celsius, in which it becomes denser than the water underneath, causing it to sink with the help of the wind. During this process, the bottom layer starts to shifting up to the top. Meromictic lakes, they also go through the same process, but it's a partial overturning only in this major layer called mixolymium. And they present a layer called monomolymium that is unaffected by the layers above throughout the year. So pit lakes are like natural lakes, but not really. First of all, they have no natural outline, so they depend on their location and how they were excavated. They can be terminal pit lakes where groundwater only flows into the pit and goes out only through evaporation, or they can be flow-through pit lakes where the groundwater enters from one side and exits from the other side. They have higher relative depths and they are narrower, and the waters are usually clear due to low concentrations of organic carbon and less microbiological activities. And they often have high concentrations of dissolved metals. With all that in mind, we have decided to do a seasonal sampling into two water profiles, one deeper and another shallower. The shallower profile was close by close to where the enterprise wants to build the heat pump system. And we sample physical-chemical parameters, major cations and ions, dissolved inorganic carbon, solid organic carbon, and stable isotopes of water. And also chosen to show you guys the sampling pictures during summer and winter periods. And based on preliminary results, we can already discuss some limnological dynamics of the pit carry. By analyzing the temperature profiles, we determined the thermocline, and it was defined where the delta T is maximum. The epilemium, which is the upper and turbulent zone with the upper boundary in contact with the atmosphere and the lower boundary in contact with the metallium, which is a temperature gradient zone. And finally, below the thermocline, we have the epilemium zone. Drawing the data, the temperature variation all over the year, salinity, ice formation, and melting, and also isotopes alongside some calculations of stability of stratification, we could define this pit lake as a mermetic pit lake, because those up layers, they are contained in a major layer that is called the mixolymium. This major layer goes through mixing twice a year, one during autumn and another during spring, before establishing the summer and winter stratification, where there's also a great variation of isotope signal. On the other hand, we have a bottom layer separated by a chemocline, which is a layer of rapid salinity change. This bottom layer is called the monomolymium, shows a higher salinity, higher density, and anoxic conditions. And the temperature is constant all over the year, where the isotope signals are stable compared to the mixolymium. And within the chemical results and regarding the environmental conditions, the light blue and transparent waters of Kerry Pit Lake shows good quality, and it's a magnesium calcium sulfate water type. We've chosen this graph to demonstrate how concentrations are constant in the mixolymium and they increase towards the bottom. The other graphs, we could establish a redox boundary according to dissolved oxygen profile and redox potential profile. There's an oxygen reduction condition towards the bottom, as well as an increasing concentrations of dissolved metals like iron, manganese, and magnesium, and also dissolved inorganic carbon. And the upper layer, on the other hand, is an environment for oxidation for iron and manganese. And what we can understand so far for the geothermal aspects is that the open pit mine have a great potential for cooling applications, and that the thermal balance should consider the energy contribution of water supply and the surrounding rock. And for the geochemical aspects is that field observations regarding mineral precipitations on the cables correspond to physical-chemical profiles that I showed you before. We were able to identify two main layers with different redox conditions as well. Finally, the thermal resource is there, but we don't know yet the relationship between effects on geochemical conditions by exploiting the geothermal energy. In that sense, the next steps for geothermal project is short-circuiting modeling to evaluate the best system configuration to minimize this thermal effect. And for the geochemistry project is to finish sampling and do some modeling in different scenarios by increasing temperature and mixing different redox conditions. And finally, do some lab experiments to verify the modeling results. Thank you. Any questions?